Hello, calculus fans! All right, so we've determined up to this point that some functions have extreme values, some don't. Sometimes if you have extreme values, you have infinitely many. So what I'd like to do is now give a theorem that gives us conditions under which we can tell that a function has absolute extrema. All right, so this is the extreme value theorem. It says that if you have a continuous function defined on a closed interval, so remember what continuous means, that there's no breaks in the graph, then the function has an absolute maximum value and an absolute minimum value at some numbers c and d in the interval. It's important in this theorem that the function be continuous and be defined on a closed interval. I think you should look in the book for some very nice pictures that illustrate the extreme value theorem. They also have some pictures of what can happen if the function is not continuous, or perhaps if the function is continuous but it's defined on an unbounded interval. Now the downside of the extreme value theorem is that it doesn't tell us how to find extreme values. It only tells us that they exist. So we're going to need to come up with some other methods to find extreme values. Now if you have a differentiable function, local extrema, they tend to happen where the tangent lines are horizontal. So if you have a local maximum, then where it peaks, then the tangent line is going to be horizontal. If you have a local minimum, then when you hit a low point, again the tangent line is going to be horizontal. And this is the case. So we can encapsulate this with something called Fermat's theorem. This says that if f has a local extremum, that is a local maximum or a local minimum at x equals c, and if the derivative happens to exist, then the derivative will be equal to 0. I might point out that you should not confuse Fermat's theorem with Fermat's last theorem, which is something completely different and has nothing to do with calculus. Now I would suggest that it's very important that we read this theorem correctly. Fermat's theorem is an if-then statement, and you can't just turn it around. So knowing that the derivative is 0 does not tell you that there's a local extremum. And I think what you want to keep in mind is the graph of the function f of x equals x cubed. Now if you take a derivative of that, we'd get 3x squared, and then it's easy to see that f prime of 0 is equal to 0. But there's no local extremum at x equals 0. So your curve can flatten out without giving you a local extremum. So in this case, what happens is that the graph is increasing, then it flattens out, and then it's increasing again. Draw a picture, see what it looks like. Now what this theorem does suggest is that we should actually look for local extrema whenever the derivative of the function is 0 or doesn't exist. Now that's where we should look. There's no guarantee that we're going to find anything there, but that's where we should look. And so the values where the derivative is 0 or doesn't exist are actually given a name because they're so important. Okay, so we're going to define a critical number. A critical number of a function is a number that's in the domain of the function where the derivative is either 0 or doesn't exist. Now it's important that the number be in the domain. We'll spend some time in some future videos doing some calculations about how do we find critical numbers. Okay, that's all for now.